Today, we're going to talk about priority queue. We know that a regular queue has a property that is first in, first out. A priority queue is similar to a regular queue, where each element additionally has a priority. In a priority queue, an element with high priority is served before an element with low priority. For example, in our case, a smaller integer means a higher priority. Then 7 has the highest priority for now. There are two ways for priority queues operation. For this one with unsorted integers, we can insert an element at the end of the queue as usual. When we need to pop an element out, we have to search through the queue and find the smallest element, which is 7, and then pop it. For the second one, with sorted integers, we pop the element as usual, which means we pop the first element in queue. So if we still insert the element at the end of the queue, the order would be wrong. That's why we need to search through the queue and find the correct place for it. To implement priority queue, we can use data structures that we are familiar with, like regular array, linked lists, binary search tree. If we choose to use array, the time complexity defined is log n, and we need O of n time to insert or to remove an element, no matter the integers are sorted or unsorted. For linked lists, it would take O of n time to find, and O of 1 time to insert or to delete. For the binary search tree, the leftmost node is the smallest and the rightmost node is the largest. If we add an auxiliary pointer to the smallest element, we are able to find the root in O of 1 time. Otherwise, we will need O of log n time to find and to insert or to delete a node. To optimize the approach, we need to understand pros and cons. For linked lists, we pop the element with O of 1 time and push an element with O of n time. If we double the number of linked lists, we have doubled places and half of time to push in elements. We also have doubled heads of linked lists to search through, which means we need double time to pop an element. If we keep adding number of linked lists, we will eventually get n linked lists, that is one element per list. We will need O of n time to pop an element and O of 1 time to push an element. We can see the relationship, that is, if we use more linked lists, time used to pop an element will go down and time to push an element will go up. In conclusion, we want only one head and as many tails as possible. What does this shape look like? It looks like a 90 degrees rotated tree. Here comes heap data structure. Heap data structure is basically a binary tree where every node has higher priority than its children. When larger value has higher priority, we call it a max heap. When smaller value indicates higher priority, we call it a min heap. Also, a binary heap is a complete binary tree. That is, all levels of the tree, except possibly the last one, are fully filled. And if the last level of the tree is not complete, the nodes of that level are filled from left to right. Now we have a min heap, and we want to insert a node 7. We first insert the node at the bottom. Next, we compare it with its parent, 25. Since 7 is smaller and has higher priority, we swap 7 and 25. And then we keep comparing 7 with its new parent, 15. We can see that 7 is still smaller. Therefore, we need to exchange their positions. This is an upward heapify. We compare the node with its parent and exchange positions when needed. If the element we insert is 3, which need to go all the way up to the root, the time complexity is the worst time complexity, which is O log n. But on average, the expected time of insertion should be O of 1. When we insert a random element into the heap, there is much higher probability of bubbling up at lower levels because the number of branches doubles as levels goes down. There is more than half of nodes that is at the bottom of the tree. Let's use this main heap again. This time, we need to remove the smallest node, which is the root. Since we want to have a complete binary tree, we're going to replace 4 with 37. Now, apparently 37 does not have the highest priority. Therefore, we use downward heapify to make it heap again. We compare node with its children and exchange positions when needed. First, we compare the children of 37. 15 has higher priority. Therefore, we compare it with 37. 15 is smaller, so we exchange them. Then, we compare the children of 37. 25 is smaller, so we compare it with 37. 37 is larger than 25, so we exchange them. When we push a new node in, the time is constant because most nodes end up at the lower levels. However, when we pop an element from the root, it's from the top and most nodes are at the bottom. The time the tree needs to traverse to maintain a heap is going to go from root all the way down to the bottom, which is O log n. Therefore, the average time used is the same as worst time complexity. The previous trees we talked about are explicit trees, because we can see that each parent has 2 children, like we explicitly built a tree before Christmas. Then after the Christmas, we need to remove the tree and store it back in the basement. In order to know how to build it next year again, we put the branches in a certain order so that we know which part of the tree it was. That is how we build an implicit tree. We put an element in an array in breadth first order. Now the question is how to keep track of each branch so that we have an implicit tree. Let's put indexes on the explicit tree so that we can see the pattern more obviously. If we have a node with index I, then the index of its parent is I minus 1 over 2. The index of its left child is 2i plus 1. And the index of its right child is 2i plus 2. You can calculate any node to verify this pattern. Now, we want to insert 7 into this implicit tree. We will first insert 7 at the end of the array and increment the index. Then, we need to make it heap again, just like we did in the explicit tree. We first treat the 7 as a child, and we find its parent, which is child, over 2. Then, we compare it with its parent. If 7 is smaller than its parent, they should exchange their positions. While the index of the child is bigger than 0 and the value of the child is smaller than its parent, it should keep searching for right position. This time, we want to pop the root from this implicit tree. First, we replace the root with the last element of the array, and we decrement the array. Next, we will perform downward heapify to rebuild the heap. Next, we will take a look at the left child and the right child. And then we will compare which one is smaller. Then, we compare the smaller child with its parent. If the smaller child is smaller than its parent, then we should exchange their positions. We will keep doing this until the end of the array. Now, we want to build a main heap from an unordered array using upward heapify. We will insert nodes into tree one at a time and grow the tree from the root. We first compare the root and its left child. The left child is 4, which is smaller, so we swap their positions. The right child is bigger than 4, so it's fine. Then we go to another level. We check 15's left child and right child. They looks good. We keep checking the child of 28. The left child is smaller. We swap 25 and 28. The right child looks good. Go to another level. There is only one child. It is smaller than 37, so swap them. Now we got a min heap. This time we want to build a min heap from an unordered array using downward heapify. We will combine little heaps together with a new root. We first look at the last little tree in the array. It has only one child. We compare 26 and its parent, 37. 26 is smaller, so we exchange their positions. Then we find a root for next little tree. Since 25 is smaller than the other child, we compare it with its parent. 25 is smaller, so we exchange them. Next, we compare the little tree where 26 is the left child. It looks fine. And then we look at the root which combines the subtrees. Its left child is smaller than the right child. The left child is also smaller than the root, so we exchange their positions using downward heapify. Since most of the nodes are near bottom, for upward heapify, which is the top-down option, some nodes need to go all the way up to the root, so its worst time complexity is O n log n. For downward heapify, every time we build subtrees, we will combine them together with a new root, which means we are going down every time. Since most of the nodes are near the bottom, it is rare that a node need to go from the top all the way down to the bottom, so the worst time is going to be O of n. This is basically all of the priority queue. If there's anything I didn't mention, please feel free to leave a comment. Thank you very much for watching. Have a nice day.